Some of these details you don't explicitly need each and every time, but when you're doing analysis using the frequency domain, you should know these properties. Okay. So, so let us understand what is the story here. Okay. Remember that we consider an image as a discretization of a continuous signal. Okay. What is that continuous signal or continuous function? You consider that the uh, object is continuous in the world coordinates, and that information is being recorded on the sensor in a digitized or sampled. Okay, so it is discretized, which means there is definitely a some loss of information. Okay, now the question becomes, how is it possible to recover the original data or recover the lost information from the sampled signal, okay, or from the discretized signal? So Fourier transform makes this possible. Okay, and so today, for the I think first 40 minutes or so, we will see how you can recover the lost data or the entire continuous signal using the Fourier transform. Okay, so that is the theme in the beginning today. It turns out that if sampling is done right, okay, done right means it follows certain rules, then it is possible to recover the original continuous function. So this is what we want to study. So earlier we studied sampling in the spatial domain, if you remember. Uh, we saw how it is sampled in the XY, how the image is sampled in the XY coordinates, and it is discretized in the intensity domain also. Right? So how the intensities are built. That is what we saw. So now we want to understand it in the frequency domain. Okay, what sampling means in the frequency domain. For this, first we need to look at a mathematical model for sampling. So this is called as sampling using an impulse train. This is what I was talking about in the previous session. The aim of the study is to understand how the Fourier transform of the original continuous data can be recovered from the sample data. Okay, so you have your sample data. From that, you try to recover the Fourier transform of what would have been the original continuous signal. Once you have this Fourier transform, you can apply the inverse Fourier transform and get the original signal. Okay. Now, in theory, all this can be done, and perfect function recovery is possible. That's what the theory we will show in theory. In practice, however, this is not always true. Okay, there are many small conditions that come into play when one wants to apply this theory in practice. But okay, let's try to at least understand the theoretical idea. Okay, how this is done, because even though in practice it doesn't work perfectly, still the same idea does go. Okay, so on the way to understanding this function recovery or function reconstruction, we will look at what is called as the convolution theorem, which sort of forms the basis of signal processing. Okay, and for since an image is a signal, so it also forms the cornerstone of frequency domain processing for us. So the convolution theorem states that if you have two continuous functions f and h, okay, or two continuous signals f and h, and if capital F and capital H are their respective Fourier transforms, then the following two pairs are Fourier transform pairs. Okay. F star H, which means F convoluted with H, and H dot F, which means H multiplied with F, pointwise multiplication. So this is a Fourier transform pair, and this is also a Fourier transform pair, which means if you multiply here and you take the convolution on the other side, notice the order of functions. Okay, if you have F star H, then you're looking at H dot F. Okay, reverse order. So both of these are Fourier transform pairs. Okay. What is it saying? It is saying that convolution in the spatial domain, small f and small h are in the spatial domain, and capital H and capital F are in the frequency domain, because you obtain capital H by applying frequency transformation to H. You obtain capital F by applying, Fourier transform to small f. Right? So this is happening in the spatial domain. So convolution in the spatial domain is equivalent to multiplication in the frequency domain. Okay. And the other way also, multiplication in the spatial domain is equivalent to convolution in the frequency domain. Okay. So this is what the convolution theorem says, and it is very useful in a number of computations. Okay. Also, this makes frequency filtering sort of. So I will go into the details a bit later, but turns out that if you want to do convolution, if you want to apply a convolution filter in the spatial domain, it is easier to oh yeah, you have a homework also based on this kind of thing. So it is easier to first transform everything to the frequency domain, do a pointwise multiplication, and then convert everything back. Okay, because the result is going to be the same. However, the number of computations required for this multiplication is much lower than the number of computations required for this convolution. Okay, so this multiplication in the frequency domain is much faster than convolution in the spatial domain. Okay, that is one of the main uses of this kind of thing. Okay, and there are many other theoretical uses also. From time to time, if you want, whenever you want to calculate this kind of thing, we will resort to calculating this, or vice versa. Okay, if we want to calculate this, you can resort to calculating this. Okay. Yeah, so we will look at this theorem, and then we will look at the sampling theorem. Okay, so the sampling theorem addresses the question of what is a good way of sampling so that function recovery is possible. Yes, this is also called the Shannon-Nyquist theorem. So I think Nyquist was the one who proposed this theorem, and Shannon is the one who proved it. So it's called Shannon-Nyquist, and we will look at this in a bit detail. Okay, so let me just so this Fourier transform pair is something that I had defined last time. So I will quickly move through this. Essentially, if you have a continuous function f small f, then you know that this capital F of u gives its Fourier transform, and the inverse Fourier transform is given by this formula. Then small f and capital F are called a Fourier transform pair. Okay. Now, the mathematical modeling of the sampling process, it can be done using what is called an impulse function. Okay, so last time I defined this impulse function. So for a continuous variable, you can define it in this way. At 0, it is infinite, and for any other non-zero t, it is 0. Okay, and it is constrained by this property. Okay, so this is the definition of an impulse function. This impulse function satisfies what is called as the shifting property. Shifting because what it does is, if this impulse is located at 0, okay, then this integral is going to pull out the value of the function f at 0. So because it pulls out the value of the function at some point, this is called the shifting property of delta, okay, or of this impulse function. So this is for continuous variable t, impulse located at 0. You could also have the impulse located at some other point. Sorry, so at location t equal to t naught. If you want to have the impulse located here, you can define it in this way. Okay, so you take t delta of t minus t naught. It is 1 if t minus t naught is 0, which means if t equals t naught, and 0 otherwise. And then this will have the shifting property that the integral ft delta t minus t naught will pull out the value of the function at t naught. Okay, so this is the shifting property of this impulse function. Okay, and that is why they are important. Later also we will see that they come into play. Okay, if you have, instead of a continuous variable, if you have a discrete variable, you can rewrite the definition of an impulse function in this. Now what we will require is an impulse train, which means not just impulse located at one point, but impulse located at many different points. So that is this impulse train. It's a sequence of impulses. So what we are going to do is we are going to separate the impulses by a distance delta t. Okay, so S delta t denotes the infinite sum of impulses located at k delta t. okay, where k goes from minus infinity to infinity. So this is impulse located at each of this is an impulse located at k delta t. This should be a capital. Okay, so you take all the sequence. This is called an impulse train. Okay, so it looks like this. This is an impulse train. So on the left hand side here, this is just the impulse. On the top, these two images are for a continuous variable, and these two images are for a discrete variable. So don't worry too much about that. We will always be working in this case. But yeah, so location T naught, the impulse located at T naught will look like this, and the impulse train using these kind of impulses at various locations will look like this. Okay. The only difference is that, when you're looking at the impulse for a continuous variable, you're defining this to be infinite. So it's like that at every spot. Whereas when you're looking for a discrete variable, you're defining it to be 1. Okay, that's the only difference. But these details don't matter much to us. Because we will always be more interested in this shifting property. And this is what we will always want to work with. Okay, so that's an impulse train. And one wants to see how this impulse train is used for sampling. Okay, so before we go there, just let's quickly look at. So this is a continuous function, right? We want to look at the Fourier transform of this impulse train. So if your impulse is delta t, then the Fourier transform of this delta t is, by definition, it is integral delta t e raised to minus 2 pi I ut dt. Right? That is the definition of Fourier transform for any continuous function. Remember, like this. And so instead of ft, now I have delta t. It's the only difference. Okay. So now if I rearrange this, I can I can bring this here and I can look at it like this. Okay. But what the shifting property of delta t says is that this thing is the function evaluated at the location of the impulse. Okay. So whatever that comes out to be, the point is that it is a constant. So the Fourier transform of an impulse is a constant. Okay. And similarly, the Fourier transform of an impulse located at t naught will come out to be this constant. Okay. And the Fourier transform of an impulse train now. So instead of just one impulse, you have an impulse train, which means you have a sum of these terms. Okay. Then you can write. So now this is slightly different, and I'm going to leave some gaps here because it's too much. So essentially, if you have this impulse train like this, you can express this in terms of a Fourier series in this way. Okay, so this I'm going to skip the details. You can find them here. But you can write the impulse train in this way as a Fourier series. And then if you apply the Fourier transform to it, then it turns out that S of u, which is the Fourier transform of small s delta t, looks like this. Okay, 1 over delta t summation. When you take the Fourier transform of functions like this, you will get delta u minus n over delta t dt. Okay. Now the only thing that I want you to note in this whole business is that if your impulse train is periodic with a period delta t, then its Fourier transform is also periodic with a period 1 over delta t. Okay. So, oh sorry, this this dt makes no sense here. Sorry. Yeah. So this is also periodic with a period 1 over delta t. Okay. So that's the only thing to remember from all this. And then, yeah, also nomenclature. This 1 over delta t is called the sampling rate. Okay, so whenever we now talk about sampling rate, we will be referring to this. Remember this delta t, what is this delta? Delta is the difference between these. Okay, where are you placing these impulses? Okay. And 1 over delta t will be called the sampling rate. So how is this impulse train used for sampling? Suppose you have some continuous function f of t, some continuous signal. You take your sorry, you take your impulse train and simply multiply it with the function. Okay, it's pointwise multiplication. So what is this pointwise multiplication going to give you? It is going to, so you can ignore this dotted thing. Okay, so we don't care about this dotted thing. They have drawn this only to show the shape is the same. But the point is that what this multiplication gives you is that at each of these locations, this is multiplied by the value of the function. So you will have an impulse of this size, right? So this gets multiplied by the value of the function. So you get an impulse of this size and so on. Okay, so these arrows or this impulse train here is representing this. Okay, and the values of the function fk, that means f at k delta t, are exactly these. Okay, so the point is that when you sample this function f using this impulse train, okay, you will have these or these function values in it. Okay, so you'll have this function and you will have these function values. Okay, so this continuous function has basically been reduced to these dots. Okay, so you have picked up the values of the function at the locations of the impulses in the impulse train. This is just, I mean, common sense. This is what we wanted to do. We wanted to discretize the signal. Okay, but this is just a precise mathematical model for doing it. Okay, and it is useful that we are writing it as a multiplication because we want to go. Remember, we want to go between multiplications and convolution when we go from one domain to the other. So that is why it is useful to express it in this manner. All right, so I hope the idea of sampling is quite clear. There isn't anything fancy about it. So now, if you want to, the idea in recovering the original signal from the sampled function is as follows. So you have a continuous function of, say, suppose you have f of t, okay, your continuous function. And then you take the sampled, okay, so this is a continuous function of a continuous variable. A continuous variable. Okay, so something like this. So you have variable t. You have some continuous function f of t. Then you discretize this using sampling, or you just do sampling with a impulse train with an impulse train, which means you have picked out certain samples of this function. Okay, and you have obtained the sampled function f tilde t. Okay, so this is what we are going to call the sampled function or the sampled signal. Now what you can do is you can apply Fourier transform to this sampled function. Okay, you apply the Fourier transform to this sampled function. Now what happens is if this distance in between impulses here is delta t, okay, then it turns out that the Fourier transform here is a periodic function, okay, with frequency related to this delta t. Okay, so it turns out that this is a some kind of, so I'll just draw something. Okay, so this is just some periodic function. Okay, so this is your f tilde. F tilde is the capital F tilde is the Fourier transform of small f tilde. So f tilde u, let's say. Okay, where u is now the frequency variable. Okay, t here was the earlier continuous variable in the spatial domain, let's say, or some other domain. U is the frequency variable. So this is u. Okay, and this is f tilde u, which is some periodic function. Now, from this f tilde, it turns out that if you choose one of these periods, okay, so let's say you choose, we will choose one of these properly. Okay, so suppose you choose one of these periods, and that is your f. Okay, so we will actually choose something centered at the origin. Okay, so not something like this, but we will, in the end, we will choose something centered at the origin. Okay, although my picture doesn't do justice. Something like this. Okay, this will turn out to be a function which is the Fourier transform of the original function. Okay, so this is an FT pair. Okay, we can show all this using uh, uh, using the definition of the Fourier transform and via this convolution operation with the sampling function. Okay, so all this we can show, but this is the idea. So now when you actually have measured something, you have this. Okay, you don't know what was f of t because you don't. There is no way of measuring this continuous signal. You only have data in the discretized form. So you have f tilde. But the point is you can recover f in this way, that you take the Fourier transform, then from that periodic function you extract one period, and that one period will turn out to be the Fourier transform of the original continuous signal. Okay. So in theory, if you know f tilde, you can recover f perfectly. In practice, what happens is, so here one of the important conditions is that it should be possible to pick out an entire period like this. Okay. Now, how these periods appear depends entirely on the sampling scheme here. We will show all this. The periods, how this appear depends on the sampling scheme or the sampling distance. Okay. So if the sampling distance is good, only then you can extract an entire piece like this, and then you will be able to recover the entire function. But if the sampling is not good, okay, then you will not be able to do this entire process. Okay, so the process depends hugely upon the sampling, how it is sampled. And then there are other small things also, or finer things, I should say, to take care of, okay, which we will not go into because that becomes too much into, I mean, it goes too much into signal processing and it's not required for us. Okay, so this one important point that you have to pick, or how this depends on the sampling, that's the one that I will talk more about. Okay, but yeah, so this sort of describes what is the general idea in function recovery. Okay, all right, so before we move ahead, we are going to need this convolution theorem all the time. So let's just quickly get through it. So what the convolution of two continuous functions is defined as? It's defined in the following way. So, oh sorry. So f star h at t is defined as the integral of, so tau is a dummy variable, f tau times h t minus tau d tau. So this is the definition of convolution of two continuous functions. And the Fourier transform of this convolution, therefore, just our usual Fourier transform formula we are applying to this entire thing. Okay. So this entire function is what is in here. You're taking its integral from minus infinity to infinity, the function times e raised to minus 2 pi I u t dt. Okay, so this is the Fourier transform of this thing. Now we simplify. Okay, so since these are continuous functions, you can do this rearrangement and change of variables. So I have just, that's all I have done here. Okay, taken the dt inside, pulled out the d tau. Okay, and since If tau is independent of t, I can pull it out here. Okay, and so we have just rearranged the terms here in this way. Now this term inside here, it looks like the Fourier transform of something, right? There is a function here and you see this term. So this looks like the Fourier transform of something. It is indeed the Fourier transform of h t minus tau. Okay, and it can be shown that is equal to capital H u times e raised to minus 2 pi r u tau. Okay, so where capital H is the Fourier transform of ht. Okay, yeah, I've written here. Capital H is the Fourier transform of ht. So the Fourier transform of ht minus tau is the Fourier transform of ht times e raised to minus 2 pi r u tau. Okay, so this shift from ht to ht minus tau gets reflected in this multiplication by this term. Okay, so okay, so let's assume that we know this. Okay, so that this is equal to hu times this. Okay, so if you just substitute all that here, uh, just a moment. I think I'm missing the term here. Yeah, I'm missing a term here. Right? I should be writing this times e raised to the e raised to minus 2 pi I u tau deta. Correct? So, well, you can pull out the hu, and then this is e raised to minus 2 pi I u tau deta. Yeah. And so this thing, okay, this term here is nothing but the Fourier transform of f term, right? So this is going to be hu times fu. Okay, so essentially what we have shown is if you take the Fourier transform of f convoluted with h, small f convoluted with small h, what you get is capital Hu times capital Fu. Okay, the product of the Fourier transforms of the individual functions in the reverse order. Okay. So this is one part of the convolution theorem, and the other part is similar. Okay, so I'm not doing that other part. I've only shown that convolution in the spatial domain is equal to multiplication in the frequency domain. I can show the other way that multiplication in the spatial domain is also convolution in the frequency domain. That is f dot h and h star f are also a FT pair. Okay, so that's the convolution theorem. And now I'm going to talk the main thing here about the sampling theorem. Okay, so all this we just saw that this is a continuous function. You use an impulse train to sample it. So this is the sampled function. This is our f tilde, right? And these are the sampled values of that f tilde. Okay. Then using the convolution theorem, if you look at the product S delta t times f, okay. So notice here that so this is my f tilde, right? So this f tilde t is ft times s delta t. But here the order doesn't matter. I could have written it the other way also. So I can also, instead of this, I can also write f tilde t is s delta t times ft, right? Then this function and the capital F and capital S, which are Fourier transforms of small f and small s respectively. So this function and this are a FT pair. Correct? That's what the convolution theorem said. So S times F and capital F convoluted with capital S these are a Fourier transform pair. That is what we do. Okay. So, I mean, remember in the general idea was that you take the Fourier transform of f tilde, right? That was what I expressed here in the general picture. We have f tilde. We want to take the Fourier transform of f tilde. So now here, taking the Fourier transform of f tilde is like taking the Fourier transform of this whole thing. But the Fourier transform of this whole thing is capital F star S, because these are a Fourier transform pair, correct? By the convolution theorem. So we just have to look at what F star S is. Okay. So well, F star S. So in the textbook, wherever I have U, they have used mu. Okay. So U and mu are sort of interchangeable in my notes. So the Fourier transform of F tilde given by capital F tilde is F Fourier F convoluted with S. Okay, so F convoluted with S, the definition of convolution is simply integral minus infinity to infinity F tau S mu minus tau deta. Okay, this is by definition. Now you get the next step by just substituting this. Okay, we computed the Fourier transform of the sample train right here, correct? So this just substituting this formula here. 1 over delta t is being pulled out and you have written all of this. Instead of u, you have u minus tau here. Now, just simplifying, you can pull out this sum, okay? So rearranging the terms, you get this. And now, see, this is again nothing but a impulse train, correct? So you can use the shifting property of this impulse train to say that this pulls out the value of capital F at a certain point, okay? And what is that point? Since this is with respect to tau, okay, that point is mu minus n over delta t. That's exactly this, okay? So, and you have the sum here outside as it is. So this integral each time by the shifting property of delta is going to be f of mu minus n over delta t, okay? So this function is the Fourier transform of the sampled signal f tilde. Now, there are a few things to note about this. Well, first thing, you can see this is an infinite sum, okay? And since this is f of these, so this is going to be an infinite periodic series, right? So this is an infinite periodic series with copies of f. This is just f evaluated at all these points, okay? And the distance, the separation between any two adjacent copies is given by this 1 over delta t. Okay. Now, each of this function, I mean, this function f is continuous. So each of this is a continuous function. And so the sum is a continuous function. So even if your original f tilde was a sampled function, discretized sampled function, its Fourier transform capital F tilde is a continuous function. Okay, so that is an important point to know. So it is a periodic, infinite sum and a continuous function. Okay. Now in this delta t is called the sampling distance and 1 over delta t is called the sampling rate. So if the sampling distance in the impulse train was delta t, then the Fourier transform of that sampled function has sampling rate 1 over delta t. Okay. Yeah, so this picture sort of illustrates what is going on. Okay, so I mean, don't look at the first part here. Let's just look at this piece. Okay, so your f tilde typically will look something like this. Of course, the shape may not be a sorry. The shape will differ. Okay, but the point is it is infinite periodic and it is continuous. Okay, so that is how f tilde will look like. Okay, now as I explained in the general idea, from this f tilde, These are infinitely many copies of f. You want to extract one copy, okay, and take its inverse Fourier transform, and that will give you the recovery of the original signal. Okay, so you just want to extract one copy of this. Now, it turns out that depending on the sampling distance, it will be decided where these copies of f tilde or where these copies of f are placed in f tilde. Okay, so now in this illustrative example, what they have shown is, suppose your function f looks like this. Okay, so capital F, suppose it looks like this. Then, because you're looking at some infinite sum like this, your f tilde will be this shape. Okay, depending on what your capital delta t was. Suppose delta t is a small value. Okay, then 1 over delta t is going to be a large value, which means the separation is going to be a large distance. Okay, and then if this is large, okay, then the copies of f mu will be placed in the, there will be a gap. Okay, the entire copy of fu might fit here, and there will be a gap between the copies. Okay, now we don't mind the gap really. What is important to us is that the entire f mu is available. Okay, so if the entire f mu is available, then only you will be able to extract it and get your original signal. Okay, now this situation where the delta t is small, the original delta t is small, and therefore the 1 over delta t, the sampling rate is large, and therefore you are able to get an entire copy of f from this. Okay, this case is called this is called oversampling. Okay, oversampling, because not only do you get the entire copy, but also there is some separation between these copies. Okay, you have more separation between these copies. Another situation in which you might be able to get this entire copy is here. In this situation, you're still able to isolate a copy. Okay, even if there is no actual separation between these copies. Okay, you're able to isolate this entire thing. Correct. This is called as critical sampling, which means it is just right. The delta t chosen is just right for you to be able to extract this copy. It's called critical sampling. And this case where delta t is large, so 1 over delta t is small. And so what is happening is that this signal doesn't fit in here. Okay, so if you wanted to fit this, what will happen is, this signal, this overlap. Okay, so because of this overlap, we don't really consider this, and the signal generated is just this much. Okay, so what it means is that in this situation, you are not able to isolate an entire copy of f. This thing you cannot isolate from this. You don't see it at all. You don't know what is happening here. Okay, this is the case of undersampling. Okay, so since our entire theory hinges on being able to extract an entire copy of f from f tilde, therefore, in this case, our theory will not work. Okay, you will not be able to isolate a copy of f, which means you cannot apply or get the original signal. So undersampling is the case in which the signal cannot be recovered. In critical sampling and in oversampling, you can recover. Okay, so what does it mean? Critical and oversampling. How do we define this? So what we'll do is this. So wherever this signal lies, okay. Suppose this lies in this interval. Okay, this interval is called a band. Okay, this is a band. So suppose this the highest frequency component of f lies over this interval. Okay, now the common sense tells us that if this interval, okay, or if this sampling rate or this distance is greater than this bandwidth, okay, then you will be able to recover greater than or equal to. this distance 1 over delta t should be greater than or equal to this distance, right? Only then you will be able to recover. If it is equal, that means in this case, right? In this case, it is this distance is equal to this bandwidth, and then you will be able to recover the entire copy. But here, this distance is smaller than the bandwidth, so you are not able to recover. Okay, so this common sense thing is what is the Shannon-Nyquist theorem or the sampling theorem. Okay, so it's saying that you can recover the signal, okay, if the sampling rate is greater than or equal to the bandwidth. Okay, so we will just give some notation for this bandwidth to state the sampling theorem. Essentially, it says that the sampling rate should be greater than or equal to the bandwidth of the highest frequency content of the given function. Then you can recover the original signal. Otherwise, you cannot. Another way of saying the sampling theorem is that it says what should be the sampling rate, therefore, if you want to recover the original signal. That it gives the answer to that. You keep your sampling. So essentially, you do oversampling or you do critical sampling, which means, oh, what does oversampling mean? Oversampling means you want your delta t to be small, which means you want these distances to be small, which means you want to take more and more samples. And this is the most common sense thing, right? That if you take more and more samples, you are more likely to recover the function. Okay, the sampling theorem only puts numbers there. Okay, puts exact numbers, puts bounds on what is the minimum requirement. But this is the very common sense thing that if you take more samples, you are more likely to recover the original function in its entirety. Okay, so the smaller the delta t, the more the oversampling, the better the chances of obtaining this entire copy of f. Okay, so that's what the crux of the theorem is. Now we'll just make it precise by putting numbers. So here I have just explained these three things: oversampling, critical sampling, and undersampling. Okay. Yeah. So if you can isolate a single copy, then you can reconstruct the original signal. So now to give a number to this interval. So the assumption is that the f is band limited. Band limited means the highest frequency content of that function is over a finite interval. That's all. Okay. Which is like saying f mu is 0 for mu lying outside an interval minus u max about the origin. Okay, so this is taken about the origin. That's all. So essentially something like this, that f mu is 0 outside this band and non-zero in here. Right? This is just a shape in this picture. The shape could be anything here. That doesn't matter. The point is it is 0 outside this band. The action is happening only in this interval. So that means it is band limited. So if f is band limited, then the length of this interval is the bandwidth. Okay. So now then since I have taken this kind of interval, the bandwidth is going to be twice u max. And what I explained earlier, the sampling theorem says that if the sampling rate is larger than the bandwidth, then you are good to go. Okay, so essentially 1 over delta t should be greater than twice mu max. That is the sampling theorem. That a continuous band limited function can be recovered completely from a set of its samples if the samples are acquired at a rate exceeding twice the highest frequency content of the function. Okay, so this is the rate. Okay. I mean, the language of this is maybe a little complicated because this comes from signal processing. So it's the language and the words used are a bit different there. But the point is this, whatever we saw here. Okay. Now, there are a few consequences of this. One, so what this is all saying is that if you have a continuous band limited function represented by samples acquired at a rate greater than the highest frequency content, whatever, that means if you follow this, then no information is lost. Everything can be recovered. Okay. Conversely, we can say that if the maximum frequency, we can say that the maximum frequency that can be captured by sampling at this rate is Umax. Okay, which means uh, that the maximum band that, so suppose you know the sampling rate. Okay, so if you know your sampling rate is 1 over delta t, then the maximum band that you can capture with that 1 over delta t is given by 1 over twice delta t. Okay, this can be the maximum bandwidth that you can capture with your sampling. Okay, that's another way of interpreting the same statement. Yeah, a sampling rate that exactly equals twice the highest frequency, which means if your 1 over delta t is equal to twice Umax, okay, then that sampling rate is called the Nyquist rate. It's just the name, and you will possibly read, okay, this is sampled at the Nyquist rate, sampled at the Nyquist rate, which means that this is being sampled at the critical rate at which function recovery is possible. Okay. Yeah, so finally, although sampling at the Nyquist rate is theoretically sufficient for function recovery, okay, sampling at the Nyquist rate will give you this critical sample. Okay, so if you sample at the Nyquist rate, theoretically you can isolate one copy and get back your signal. But in practice, it is not, this doesn't happen. Okay, in practice, there can be problems for certain functions. There is an example here that illustrates exactly how the problem can occur. So in general, it is recommended that the sampling rate should exceed the Nyquist rate. Should not be equal to the Nyquist rate, but should exceed, so that you end up in a oversampled situation rather than a critical sample situation. Okay, so always this is the situation that is preferred. Okay, so now you have your capital F, okay, and you want to recover uh, the original signal. Okay, sorry. So yeah, I didn't still talk about how F is recovered or how one copy you can recover. So this is done by a box filter. So again, this is a multiplication. The figure illustrates it all. So you have your F tilde copies, okay, oversampled situation. You want to isolate this piece, okay. You multiply it with a box filter. This is called a box filter. So this is 1 in this interval. So if this is 1 over delta t, you look at the bandwidth, you define h mu to be 1 over that band, 0 everywhere else. Okay. And you simply multiply. So fu is going to be f mu is h mu times f tilde. So this box filter times this is going to give you your required f mu. Okay. So that is the mechanics. But essentially, we are trying to isolate a copy of it from this. The way it is done is like this. So that's that. And now you have to apply the inverse Fourier transform to this to get your original continuous signal f. Okay, so that is this step. In theory, f is recovered perfectly. Okay, you have your continuous f in this way. In practice, one does not do it this way. Okay, in practice, what is done is notice that, so this tau inverse that I have written, or maybe I should write f inverse, because what I want to say is f inverse denotes the inverse Fourier transform. Okay. In practice, notice that small f of t is what is the inverse, the inverse Fourier transform of capital F. Capital F was h multiplied by f tilde. So the inverse Fourier transform of this product is same as ht convoluted with f tilde. right? Because multiplication in the Fourier domain is convolution in the spatial domain. So this and this are a FT pair. Okay, and now so this the way this is computed. So I haven't written all the details. I can. So I didn't also provide reference, but I can provide reference. The point is that this evaluates to all this. Okay, where sine c is this function. Okay, I'll give you a reference. But the point now is that so f of t is this infinite sum. Okay, so in practice one doesn't do this integration, but one uses this formula, and f and t are actually the sample values at the when n is an integer. Okay, that f n delta t is exactly these sample values. These we know from the sample function, right? So when n is an integer, sorry, when n is an integer, then we know these values. Okay, uh, and when n is not an integer, okay, one uses interpolation using this function. Okay, the values between integers are interpolated using this function. So the point is that the function recovery is not done like this as integration, but it is done by interpolation in practice. That is the point I want to make here. Okay. All right. So that is also one more reason why so I skipped this, but I need to go back to it. We want to understand what is interpolation, at least in the case of binary and like binary interpolation and bicubic interpolation. Okay, so one of those methods is used to recover the actual function f. Uh, so if you, I'm sure you will have questions, but if you have a quick question that you can ask now, you can go ahead. So you are not expected to know all the details of this, but the highlights of this theory. Okay, what are the or how actually you should be able to explain how this process goes through. Okay, this idea that I explained up here. Okay. So if you can understand this entire idea and little details of how every step goes through, that is what is expected of you. Okay, you don't need to go through all the mathematical details of this. It's not required at this point. Uh, all right. So moving ahead, I want to talk about the effect of aliasing. So what is aliasing? And so remember, see, all of this we saw for a one variable case. We are doing all this in one dimension for now. Okay. But really an image is a two-dimensional function. Okay. So all this we will, I want to carry these ideas to two dimension, but in two dimension doing all this, whatever I showed you here, okay, or whatever all this analysis that I showed you, it is difficult to show like this in two dimension. Okay. So if you understand these ideas in one dimension, you can imagine how it will be in two dimension. Okay, and if you understand what is aliasing in one dimension, then you can understand the effect of aliasing in images. Okay, so that is the thing, that sampling and aliasing we are doing in detail in one dimension, but two dimension we will say that these ideas will just carry over uh, just like one dimension. Okay. Okay, so aliasing is an effect that occurs due to undersampling. That is the main thing. If you have undersampled, then something like this occurs where you have one signal, but it appears as another signal. Okay, so here, so the best way is to look at pictures. So here, this is the signal. This is the actual signal. Okay, so this has these peaks and placed quite closely to each other. Okay, now you have done some sampling. Okay, sampling is being done at, see, this distance. Okay, so some sampling is being done. At that sampling, at that distance, the samples being picked up are these. Okay, so these are the samples picked up from this function. Now you have another function here, also sampled at the same rate, and so you will have these samples picked up. But look, when you're doing, when you have already the sampled information, you don't have this. Okay, you don't have this original signal. You only have this right hand side data. Okay, now the right hand side data looks the same for both signals. So there is no way of knowing from this right hand side data what was the original signal, right? Was it the signal on the top here or was it the signal here? You cannot tell. Okay, so again, this is a common sense thing, but this has very interesting effects. Okay, but the point is this. Okay, that if you undersample, then your signal, original signal, might appear as another signal, or if this was the original signal, you might think it was this. So it is possible that two different functions generate the same sample function. Okay, and when you do function recovery from this sample, you don't know which one it was. Another way in which this can be interpreted is the following. So now, again, I'm looking at this original signal, and these are the sampled points. Okay? Look, the sampled points have a shape of themselves, their own, right? Just look at these dots, and they form a shape of their own. So again, if this was your sample, you might as well think this, the original function looks like this curve that I am tracing out with the pointer here. Okay, so the original function is being sampled as this function. So that is why it's called aliasing, because one function is sort of showing up as some other function. Okay, so there is a false identity. That is why the effect is called aliasing. Okay, so one function being sampled as another function.